Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another week of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are just entering our fifth week of this course, and just to commemorate the finishing of 4 weeks or 1/3 of what this course is supposed to be, I have changed our background to a very nice SpaceX satellite, which is orbiting the Earth. Until now, we had this nice background of a rover on Mars, and we said that you use these autonomous algorithms to determine where the rover is or its position and where it's supposed to go, and there are algorithms that drive the rover in a particular path. All right, because it cannot necessarily be remote controlled in real time from the Earth. Right? Similar situation is that for spacecraft also. Yeah, a lot of what we do in adaptive control uh, has to some extent been implemented in by the spacecraft community, by the satellite community, and so in order to maintain both the position of the spacecraft in orbit and also its orientation in orbit, right, which may be a rather mission critical component, we at several occasions require the use of adaptive control, because it's not very easy to figure out several space parameters like the inertia, mass, etc. of these spacecraft, which are also, of course, losing fuel at a pretty good rate as they are flying. Yeah. So anyway, so this is another motivating application for us. In fact, a lot of my own work in my PhD in aerospace engineering was in fact using adaptive and nonlinear control to spacecraft problems. All right. So anyway, so hopefully again we will continue to see this background for a while, and hopefully we can motivate ourselves to design and develop algorithms that can drive systems such as this spacecraft. All right, excellent. So what were we doing until now? Right? So we were actually somewhere here, right? We had not finished the lecture notes from previous week, in fact. Yeah, and this is why I had mentioned that we should not worry too much if we are sort of moving ahead in the lecture notes, because I knew that as we move forward, the material will get more involved and we will start to get a little bit slower. Okay, right. Uh, right. So, but by now, I think most of you understand what is the notion. What are the notions of stability? What is the pitfalls in analysis? How to sort of we had a grip of how to use the Babolat's lemma. We also are now looking at the Lyapunov stability theorems. All right, so we've already looked at the stability theorems until global uniform asymptotic stability. So now we are left with only the exponential stability theorems. So as you all might recall, exponential stability essentially is a more advanced version of asymptotic stability, I would say. And why is it more advanced? It is so because it actually gives you a particular rate of convergence to the equilibrium, which is assumed to be the origin in almost all our problems. Okay, so that's the idea of exponential stability. So the question is, what do we require? Yeah, what do we require for exponential stability? So we already have our usual assumptions, right? That we need to have a candidate Lyapunov function, which means that it is a C1 function, which is positive definite. Okay, so this is the least that we do require. All right. Um, Beyond that, we require V to be decrescent, right? Because these are the properties that you have already started to see appearing. So we require V to be decrescent because exponential stability is by definition also uniform, right? So V is required to be decrescent. Further, we require three class K functions, all of the same order of magnitude. We will talk about what this means soon enough. Same order of magnitude, right? We'll talk about this soon enough. Let's not worry too much about what this means. But we require three class K functions such that V is bounded on both ends in this way. In fact, although I have mentioned V is decrescent, but if you look at this particular if you look at, in fact, let me be careful here. This is not really required. There is no time argument here. Okay, there's no time argument here. The third one is fine, but here there is no time argument. Okay. All right. So what we, if we look at this left hand side, this, what does this mean? This means that V is positive definite. This is requiring V is to be positive definite. If you look at the right side inequality, this implies that V is decrescent. Yeah, so this is not actually required. So if I can sort of say this is implied. Yeah, and this guy, this implies, in fact, I should be careful. I should say it's a one-way street. Of course, this implies that this is positive differential. And further, the third requirement is something like this, that V dot is less than equal to some negative of class K function, right? Now this again, okay, so here also, of course, we don't need this time argument, right? Let's be careful. Time argument is not needed. V dot is what we have defined already. Yeah, it is the Lie derivative or the directional derivative of V, right? And this particular piece, yeah, this means what? This already means, implies, I mean, not means, but this implies negative definiteness of V, of V, of V dot, sorry. Yeah, so if you look at it, it seems like everything that we require here is already being mentioned here. Well, I'm sorry, everything that's required here, because looking at the local version, is already being mentioned here. That V being positive definite is part of the candidate Lyapunov function definition. Right? V being decrescent is mentioned here, and V dot being negative definite is mentioned here. So it looks like the conditions are exactly the same. All right, but there's a very nice and subtle little difference here, and that is these words: same order of magnitude. Okay, this is the difference: same order of magnitude. So here we did require class K functions to claim all of these, but we didn't say anything about them being the same order. But for local exponential stability, we do require them to be of the same order of magnitude. All right, so this is important. Let's try to remember this. Okay. Now the global version, of course, it moves from V being positive definite to V being radially unbounded, and of course, you will also require that V be valid over the entire domain Rn. Yeah, unlike what's specified up top. Right? So we require this also. And we require this also, that V be valid or V be defined in the entire domain. And of course, we need now class KR functions, 3 class KR functions, all of the same order of magnitude, such that you have the same type of inequalities. Yeah, I mean, I will again remove these. When you're doing this comparison, there is no time. Yeah, because we are not, when we do these comparisons, we are not looking at X as a solution of a dynamical system, but X as just a variable. All right, so it's not appropriate to put a time argument in here. Okay, and so if this happens, so if you have radial unboundedness for V, yeah, and you have 3 class KR functions, then you of course you get something like global exponential stability. All right, okay, so this is the notions of local and global exponential stability. All right, so let's sort of try to see what means for functions to be same order of magnitude. Okay, so we say that two functions in reals, so here we are talking about fy and gy mapping to the real numbers, they're said to be the same order of magnitude if they are comparable using scalar quantities. That is, if there exists some scalars gamma 1, gamma 2 positive, such that G is bounded on both sides by F scaled by these gamma 1s and gamma 2s, and vice versa. Okay, and vice versa. Okay, because if you see, if this happens, then the flipped version can also happen, right? Because from here I can also say that, so this also implies, if you notice, that I can write Fy bounded on both sides um, 1 over gamma 1 gy and something like 1 over gamma 2 gy. Okay, so this is equivalent, right? These are equivalent. Okay, so if basically one function can be bounded on both sides by the other function, then the converse is also true. All right, should make sense. Yeah, so two functions are said to be of the same order of magnitude if they can be compared with each other by just scalar quantities, scalar constants. Yeah, scalar constants. Yeah, not functions of state, not functions of time. Okay, scalar constants. Okay, so for all the above theorems, so this is what it means for the same order of magnitude. So for all the above theorems, we say that if V satisfies any of these theorems, it is said to be a Lyapunov function. Then that particular V is said to be a Lyapunov function. If it satisfies any one of these, yeah, so any of one of these bullet points, many bullet points, then it is said to be a Lyapunov function, not a candidate Lyapunov function like here, but a Lyapunov function. So although we don't talk about it, but they do exist converse Lyapunov functions. Yeah, and the statements always go something like this. If x equal to 0 is stable for some system star, then there exists Vtx positive definite such that, yeah, positive definite and C1 such that something happens. Okay, so this is what the converse statements look like. Yeah, the converse statements essentially say that if your system is stable or asymptotically stable or exponentially stable, then you're guaranteed to have V with these kind of properties, with the with the properties that we are talking about. Yeah, that it satisfies one of these bullet points. Okay, so there do exist converse theorem. Yeah, there do exist converse theorem, but of course it is not a constructive evidence, right? So just the existence of a converse theorem does not mean you can find a Lyapunov function. It's not always easy to find such a Lyapunov function. Yeah, just using the fact that there exists a converse theorem. Yeah, so this is the unfortunate truth. So that's why we're not really stressing too much on it or actually stating these theorems. Okay, So there's an example that we want to do now, but before we move on to the example, I want us to look back at the previous examples and see if there was any system which was already exponentially stable. Okay, so we did a few examples, right? If you look at, let's see, did we do a, right? So here, no, this was a harmonic oscillator which was just stable. Then we did, okay, I mean, we could not talk about stability. It was in fact unstable. Then we found a non-uniform stable example. Then we did this example, right? This is the damped harmonic oscillator, if you may. This is a damped harmonic oscillator. All right. And what did we actually do? We took a Lyapunov function, which is something like this, right? Which is kx1 plus x2 squared by 2 and x1 squared by 2 alpha. And we could show that v dot is also the same in some sense. Okay, v dot also has kx1 plus x2 square and x1 square. Okay, it has the same terms as this guy, kx1 plus x2 square and x1 square. Right? And from here, we claimed global uniform asymptotic stability. But the fact is that this is also globally exponentially stable. Yeah, why? Why? So the first thing is that V is positive definite. And it satisfies all the properties, right? So in fact, V is radially unbounded, not positive definite. V is radially unbounded. Okay, and so V is lower bounded by a class KR function. Similarly, V dot is also radially unbounded, right? Because it has the same terms as this. If this is radially unbounded, V is radially unbounded, then V dot is also radially unbounded, right? Therefore, V dot also is upper bounded by a class K function, right? Because it is a negative sign, right? So it's upper bounded by a class K function, and of course decrescence is free because there is no time argument, right? So therefore it is also upper bound. V is also upper bounded by a class K function. So V is both upper and lower bounded by a class KR function, and V dot is upper bounded by the negative of a class KR function. Okay, so this is one of the things. The next thing is same order of magnitude of these functions, right? Same order of magnitude. So what are these class KR functions in fact, right? So if I look at what these class KR functions will be, in fact, I will take exactly this function itself as my class KR function. Okay. So if you notice, I had this phi 1, phi 2, phi 3 in class KR. So here I will take my, if I may, let me make it bigger. I will take my, let me write in some other color. Actually, I will take my phi 1 as half kx1 plus x2 square plus 1 over 2 alpha x2 square, right? Which is exactly v. Okay, sorry, this is actually x1 square. Okay. So this is also the same as phi 2 and this is the same as v, okay, because I can use the same on both sides. And phi 3 I will use as this guy, minus 1 minus k kx1 plus x2 whole square, no minus actually, not in the class K function, plus k over alpha x1 square. Okay, this is what I take as my phi 3. And if you look at phi 1, phi 2, phi 3, first of all, these are radially unbounded functions, right? This is not difficult to verify. They're positive definite, right? How are they positive definite? We've already verified this is positive definite earlier, so I don't really need to do anything, right? Because this was already done. I don't want to repeat it, and you can see from here. Now, radial unboundedness is obvious because if x1 and x2 go to infinity in any direction, okay, the only problematic direction would have been just a second. Only problematic direction would have been when kx1 plus x2 is 0. But in that case also, x1 is going to infinity still, because if x1 and x2 both have to go to infinity in some direction, right? So the only problematic direction would have been where this is 0. But then x1 is still going to infinity. So this whole thing is going to infinity. So these are in fact class KR functions, no questions asked. All right. Now, the fact that they're same order of magnitude is also very straightforward to verify. You can see that they're just related by some constants, just different constants. These constants are the only things that are different. Okay. So it's very easy for me to relate phi1, phi2 and phi3 by some. In fact, phi1 is equal to phi2. So the constants are 1. To relate phi1, phi2 and phi3, I just need to find another constant, right? Which is very easy because they're just multiplied by some constants here. Okay. So that's it. So this is in fact turns out to be globally exponentially stable by this argument. Okay. So we've already seen an example of global exponential stability. Now, if you look at this guy on the other hand, right, this pendulum or a variation of the pendulum example, in fact, right? If you look at this example, it is uniform asymptotically stable, but it is not even globally uniformly asymptotically stable because this is not a radially unbounded V. Okay. So the question is it locally exponentially stable at least? Is it at least locally exponentially stable? Would be the question, right? This is not very easy to verify. This is not very easy to verify because what we have to do is now compare this guy and this guy. Compare this and this. Yeah. Now comparing this and this is not easy because if you look at, actually we are going to compare the particular class K functions that bound these. But even if I try to compare these two quantities, see x2 is the same, right? It's the same function just with different gains. So this is not a problem. But this one, okay, could be a problem. This one could be a problem because at x1 equal to, right? So say at x1 equal to pi, what happens? Let's see what happens. At x1 equal to pi, what happens? Actually, we are not including pi, so we might still have some chance. Yeah. But this is not very obvious a case of same order class K functions. Yeah. In fact, there is a trigonometric formula for 1 minus cos x1, which is, I think, sine square x1 by 2, I believe. Yeah, I think it's sine square x1 by 2. I will have to verify this though, but I believe it is sine square x1 by 2. But here I have sine squared x1. Yeah. So we still have to see if these two actually have some kind of an exponential connection with each other. Have a same order or a scalar connection with each other. Okay. And this is not super easy to verify. I can tell you that. Okay. So it's not very clear if this is in fact locally exponentially stable or not. All right. For almost certainly it is not. Yeah. All right. But I will leave all of you to think about this and argue this. Okay. It's a very interesting question. Is this so the question we are asking is this locally exponentially stable? All right. Great. Now that we have seen this, we want to look at this, very nice tiny little example, right? So this is the system which is, highly nonlinear, right? It actually looks like an oscillator, harmonic oscillator until here, but then you have some nonlinear terms multiplied by a constant c. Yeah, some constant c. Yeah. Now we take a very, very simple candidate Lyapunov functions, x1 squared plus x2 squared. Obviously, this is positive, definite, radially unbounded, and all the good things. Yeah. And then we take the derivative as always. Okay. We are trying to do a stability analysis. So we'll take the derivative. Okay. What happens? X1, x1 dot. I get, x1, x1 dot and x2, x2 dot. And then I simply plug in from here. Okay. It's pretty straightforward. This basically it's a harmonic oscillator, so these two terms obviously cancel out. They do in all of our examples if you notice. And then these two start to look the same. C x1 square plus x2 square, C x2 square x1 square plus x2 square. So actually if you combine them, you get something like this: C times x1 squared plus x2 squared whole square. Now, if you want to conclude negative definiteness of V, it is the minimum thing we would want to do. We want to conclude negative definiteness of V. Yeah. First of all, then okay, let me continue. Then we would require C to be negative at least. If C is positive, then there is no scope of V dot being negative definite. It should be obvious to you, right? Because this quantity is positive. In fact, this quantity is also radially unbounded. Okay, this quantity is also radially unbounded. How? You can simply see this by looking at this. It's greater than equal to C x14 plus x24, but it's actually equal to this plus 2x1 square x2 square, but this is already greater than equal to 0, so I can say this is greater than equal to C x14 plus x24, which is of course radially unbounded, right? Or the negative of it is radially unbounded, right? So depending on the sign of C, right, if C is positive, well, wait a second, I think, yeah, if C is negative, in fact this is not correct. There should be, if C is negative, if C is negative, then V dot is actually negative definite, in fact radially unbounded negative definite, and therefore the equilibrium point, that is the origin, is globally uniformly asymptotically stable. Okay, but if C is positive, then 0 is unstable. We will need something called Lyapunov instability theorems. Okay, we can actually show that the origin is unstable if C is positive. Yeah, but we will need Lyapunov instability theorem, which we did not state, but that's part of your exercise. Okay, that's part of your exercise. You have to find the Lyapunov instability, an instability theorem, and use it to show that this system is in fact unstable at the origin if C is positive. All right, right. Now, if C is negative, one might even ask, why is it not exponentially stable? If you look at this function here, this is radially unbounded. This is also radially unbounded if C is negative, so in the negative direction. So V dot minus V dot is radially unbounded, right? But if you look here, what are the class KR functions? So again, phi1 equal to phi2 will still be half x1 squared plus x2 squared. Since there is no function of time, I can directly use this. This is a class KR function, right? And phi3 will unfortunately be something like minus modulus of C, because C is negative, x14 plus x2 to the power 4. Now notice that this are different powers. They're similar looking polynomial terms, but they have different powers. So you can never compare them by a constant, right? Because what will happen as x1 becomes larger and x2 becomes larger, this will become significantly larger than these terms. Yeah, and you cannot compare them by the same constant anymore. Notice, I only get to choose a single constant to compare these class KR functions with. Yeah, that is, I can only, oh, I'm sorry, I think it's right here. Right. I only get to choose this gamma 1 and gamma 2 for all, one gamma 1 and gamma 2 for all y. It is not a function of y. Yeah, but I cannot do that in this case. Yeah, because x14 will start to dominate x1 square significantly, and similarly x24, right? And therefore there is no way that they are so they are not same order. Yeah, therefore there is no way I can get exponential stability. All right, but I do get global uniform asymptotic stability. All right, great. So what have we looked at today? we sort of wanted to complete our discussion on Lyapunov stability, and we have done that. So we were left with exponential stability theorems. So we looked at local exponential stability and global exponential stability, both of which augment asymptotic stability in the sense that they give you a rate of convergence. And this requires us to know about same magnitude class K and class KR functions. So we did define that. Yeah. We also look back at our examples to see which ones of the examples we had already seen were in fact um, exponentially stable, and we found that the damped harmonic oscillator was in fact exponentially stable. Right? We also looked at a new example, uh, and you have an exercise, of course, and we saw that this new example, of course, is not exponentially stable, but can be globally uniformly asymptotically stable if you have an appropriate constant C. All right. Excellent. So we will continue. We will look at a slightly more involved topic here on, and it basically sort of takes the knowledge of persistence of excitation to talk about new exponential stability theorems for linear systems, and that is something that's rather useful in adaptive control and parameter convergence analysis. All right. Great. That's all for today. Thank you.